All right. We're recording.
Says it's recording.
Yep.
Okay. Good to go. Yeah. How do we do that? How do we lower the lights a little bit? All right, how is everyone doing? Good? Thumbs up? All right, I just want to make sure that we all give ourselves a round of applause for showing up. Give yourself a pat on the back. It's kind of cold out there. So I want to thank everyone for coming. Just a little bit of special thanks. I'm just going to kick things off for us before Chris takes the mic. I just want to say a special thank you to Kira Frank, Matthew Hart from event planning. I want to thank all of the DACEs and the FSRs for helping out, the entire Google community who was involved. I also want to thank Chris Moniak for helping with his brilliant idea of having this event. Faraday for coming and volunteering to talk about their experience with BQ. Quantiphi for helping to organize the event and providing refreshments for us all. And all of you for taking time out of your day to help out with the first Cambridge Data Meetup event. So the topic for today is BigQuery and BQML. The agenda will be Chris will come and he's going to talk about use cases with BigQuery and BQML. Then we'll have Faraday come up and chat about more about their experiences and how they use BQ in a productionalized environment. And then we have these lovely chairs up here to have more of a very conversational fireside chat about the product. Please ask what's on your mind in terms of questions that you've had about BigQuery, even about Google Cloud Platform in general. This is a very open dialogue. I want to stress on that. We wanted to create a safe space to talk about our products and really hear from you, the customers, and also customer type of the engineers about questions you may have or how to best utilize the product and best practices. So without further ado, I'll introduce Chris Moniak to talk more about BQML. Thank you.
Thanks, Chris. So today we're going to talk about BigQuery, BigQuery ML. Quick agenda on what I'm going to show. So I guess let me first introduce myself a little bit more formally than just being Chris. So I'm Chris Moniak. I'm a customer engineer here at Google Cloud. I am somebody who helps out customers like you all when you're trying to decide what sort of architecture you're looking to build your data platforms with, when you're trying to basically stand stuff up for the first time. I've been here for about 3 years now. Previous to here, I was at Snowflake for a little bit less than a year, and then I was at IBM for almost 7 years. So all my time in sales engineering has been in data warehousing in one form or other, which is why I'm here to talk about BigQuery. So I'm going to go quickly into just a quick overview of what Smart Analytics is on GCP. I'm going to go into then an overview of what BigQuery is, some of the storage and ingestion methods that we have. Then we'll go into how do you actually query data inside of BigQuery. And after that, Faraday will talk about how they use BigQuery in their day-to-day lives and how it's made their business able to grow to the point that it has. So let's get started. The promise of data, AI, and analytics is undeniable. It's the reason that we're all here today to see this presentation and to hear us talk. Organizations today understand that there's tremendous potential in harnessing the power of data and machine learning to create compelling customer experiences to optimize operations and get ahead in the marketplace. By now, companies in all industries have realized that in order to compete in a fast-moving environment, fast transforming in a fast digital world that we're in, that companies that were traditionally not data companies before have become data companies. There is still a lot of difficulties that are involved in this process of being more of a data-driven, AI-focused company, organization. And very few companies actually achieve 100% of that benefit from AI. So why are organizations unable to tap into the potentials of AI? This is what we're gonna take a look at. In the past decade, of course, we've experienced an unprecedented growth in the volume of data that can be captured, recorded, and stored. Maybe a few decades ago, terabytes worth of data was huge for data warehousing. Now we're talking about petabytes on a normal day-to-day scale. And some of our larger customers on BigQuery are actually in the exabyte scale of data. But it's not just the volume or the growth of the data that's a problem. It's the nature of the data itself. So now, maybe 10 years ago, all data was pretty much structured. You had some JSON, you had some XML, but now data is coming in all sorts of shapes and sizes. The bottom line is that data is limitless, but most data platforms aren't limitless. So even those that are quick to set up and demo, you could do a quick spin up of a 10 terabyte data set and everything's fine and dandy. But once you get to more petabyte scale, that's when like traditional data warehouses start to tend to fall apart. Second, the way that we've worked with data is continuing to expand. There's no longer like one simple way to work with data. So whether it be machine learning frameworks, various programming languages, real-time stream processing, or even data-rich, intense applications. It's not about just one API or a framework anymore. The workloads that we have are truly becoming limitless and coming together to operationalize innovation. Third, our data reaches about everyone nowadays. So not only all of our employees, but all of our customers, partners, suppliers, and through smart applications, analytics, alerting, all the data networks that the data needs to interact with. That's pretty much, it touches every aspect of our lives. So here's the reason why we believe Google Cloud is uniquely positioned to help solve this problem. Because we as a company in Google, we live it every day and we've lived it for decades. I mean, Google at its core is a data company. We collect data, we use that data to position things like on the Google ad side to best position which ads would fit for a certain customer. And we've been running big data analytics based off of that data for decades now. Google's Data Cloud is one of the most comprehensive and complete unified data and AI solution provider in the market today. The ability to manage each stage of the data lifecycle across data warehouses, data lakes, and rich data-driven experiences, break down silos and unlock innovation in AI and ML. The Google Smart Analytics platform is a flexible, open, and secure analytics platform that provides the easiest path to becoming an intelligent, data-driven organization. It's built off top of the decades worth of innovation and research that we've done internally. So like I said, we've been doing this for decades, and we, over the past 5 or 6 years, have really made it a point to say, well, we're taking advantage of all of these tools that we're using. Why can't the general public take advantage of it? Smart Analytics platform lets you analyze data at a planetary scale with serverless experience. So no more worrying about operations on spinning up compute, maintaining infrastructure. It's truly as easy as it gets. So we're significantly simplifying data analytics through each of these pillars that we have outlined on this slide here. We deliver serverless analytics. We allow customers to keep their focus purely on the analytics versus worrying about the infrastructure. We've got a comprehensive set of data analytics workloads, from data warehousing to streaming to business intelligence, and we let our customers operationalize machine learning. So one of our customers, Faraday, is going to talk about how they've been able to use machine learning to grow their business through the data that they have. The 5 design principles we have here. Serverless, so a lot of our products are completely serverless, so you're not having to deal with maintaining the infrastructure. You're able to focus more on actually providing value of the data that your business collects. An end-to-end machine learning lifecycle. So we let our customers operationalize machine learning. Because we make machine learning easy, it's easy to integrate into your applications and into your workflows, where traditionally having to move data outside of the data warehouse causes bottlenecks. It causes both cost in time, performance, and actual monetary costs, where with us, we're building that directly into the platform and making it simple to use. Real-time analytics. So the ability to stream data into a data warehouse like BigQuery in real time can be a game changer. There's some other competitors that are quasi real time, where the data lands and you could query it within a few minutes, where when using stuff like our storage API and streaming pipelines, you're able to actually query the data as it's coming in on a row-to-row basis. So if you have some very low latency requirements on doing analytics, like maybe certain like alerting, where for like a hospital kind of a use case where you're constantly looking at maybe baby monitor data, and you need to do analysis that says, okay, if this anomaly pops up, make sure that you ping the nurses station as soon as possible, because historically we've seen that this is a cause for concern. So real time, and I mean by the seconds real time, can be a matter of life and death in those kind of situations. Analyzing data anywhere. So we're not only limiting you to analyzing data that's in Google Cloud, we're giving you the ability to analyze outside of the cloud in data that's on S3 and Azure Blob, being able to connect up to those environments. We don't want to be a walled garden where we're locking people only into our platform and then giving them a choice. The way that we look at things is that if you have the right tools for the job and you're using them, you're getting value out of them, that's all a plus for us. So there's many services and components within the Google Smart Analytics platform that enable users to collect, process, store, and analyze their data at scale and in any format, that using both batch and streaming ingestion. We've got orchestration services that can automate the end-to-end data processing pipeline. So like the serverless stuff that I mentioned before, you're basically just setting up the pipeline, letting it run and not having to watch it. We've got a bunch of services, even like that I'm showing here, but we're going to focus mostly on BigQuery for today. So that brings me into talking directly about BigQuery. So BigQuery is Google Cloud's highly scalable enterprise-grade data warehouse solution. It's fully managed and serverless, and it offers real-time insights from streaming data, has built-in ML capabilities, and it has a high-speed in-memory BI engine for faster reporting and analysis. BigQuery is designed to make data analytics and data science more productive, and it's a secure offering that has data encrypted by default to ensure that data security is met. There's a few unique features that BigQuery has. So BigQuery is the industry's first truly serverless and managed analytics solution with planetary level scalability. Like what I talk about serverless here is that you're not spinning up compute for certain workloads. You're basically just submitting your queries to BigQuery, and our fully managed backend is what handles the actual scaling of that. And I'll go into that a little bit further on. True real-time analysis to let you query and analyze within seconds. So like that baby monitor use case I was talking about, out-of-the-box machine learning capabilities. So folks like citizen data scientists and software engineers, they're able to train and run high-quality machine learning models easily through just a SQL interface. You don't need to have to learn Python. If you're familiar with how to write SQL, it's basically just a create model, give it the model name, some of the parameters, and then do a select statement off of the data that you want to run the model off of. It's just that simple. The BigQuery BI engine, it's a fast in-memory analysis service that lets you return queries in a sub-second manner. So this is for something that, say, like you have a very low latency dashboard that gets updated very, very often. And you need those sub-second query response times and high concurrency. This BigQuery BI engine is what you would use for that. BigQuery is more than just a data warehouse, though. It provides you with a foundation needed to approach data and serve your customers in new ways. So from storage to computing to networking, BigQuery is designed to bring all of Google's innovation and resources at the service of your queries. So BigQuery itself, it's based off of a storage system called Colossus. So that's Google's global storage system, which handles all of the replication, the recovery, and distributed management so that there's no one single point of failure. And because it's fully managed, the storage isn't something that you're not spinning that up. You're not deciding that, oh, I want 10 terabytes worth of storage. Basically, it starts off from nothing and can grow to quasi-infinite scale. Obviously, if you're storing all of the knowledge of the world and trying to put that into BigQuery, that might make our stockholders happy, but it's probably past exabyte, whatever I don't know what's higher than an exabyte, but let's say 10 exabyte, call it that. Google Borg, so like in the sci-fi world, it's our cluster management system. So what that does is it automates and routes all the tasks and jobs. So it's distributing your query across thousands and tens of thousands of servers to get you your response to those queries back. And Google Dremel, which is what the BigQuery execution engine is, it's completely stateless. So what that means is that if one of those Dremel nodes or even an entire Dremel cluster goes down, the queries that you have running don't get interrupted. Basically, the workers will then take over whatever failed and just hand that off to the next available worker. So some other sort of like Netezza, where I came from, if something were to break down and fail, it would just kill your query. So if you had a query that runs in 4 hours and it dies in 3 hours and 59 minutes, you have to run that thing over again. Or with BigQuery, because we have the resiliency, one little portion that dies basically just gets handed off to somebody else. And when you combine that with Google's Jupyter, which is our high-performance networking infrastructure, you'll find that BigQuery is 10 times more reliable than the average cloud data warehouse product. BigQuery is more than a cloud data warehouse. It's a platform for innovation, and it's a platform that treats data and analytics as a business critical capability. So it's important that we reiterate on the importance of serverless. It's a completely different approach to analytics. So rather than thinking of managing the infrastructure, we're shifting your focus completely to the analytics that you're trying to derive from the data and removing the conventional steps of having to involve IT or operations in a data warehousing project. So there's three foundations that we're trying to build into each of our products. One is the ease of use of setup. So big data can be difficult, and we talked about some of the reasons why it's traditionally difficult. We're providing the industry's only no-ops big data platform. And for here, we mean, with no-ops, we mean the application developers never have to speak to IT if they don't want to. They just have access to their data. They could run their queries. They don't have to worry about the actual availability of compute and storage and things like that. Speed of iteration is number two. So what that means, what the best way that I've always described this before is failing fast. So like that example I gave you before, if something runs in 4 hours and okay, if it completes and runs in 4 hours and it's not the answer you were looking for because maybe the parameters were a little bit off or your filter conditions weren't exactly perfect, you basically just wasted 4 hours. With something like BigQuery, because we have all the horsepower of tens of thousands of servers behind it, you're going to get your queries back a lot faster, which is going to allow you to just continuously build and iterate upon your analysis. And third, and not lastly, but low total cost of ownership. Because we're a fully managed big data solution, you're not having to deal with additional headcount for maintaining a system like BigQuery. Because all you're doing is basically just loading up the data and running queries, you're able to save on costs, both on a manpower situation and as well as actual financial costs of running the service itself. So you're either paying for the bytes scanned and storage, or there's another model where if you start to get above maybe like $10,000 a month, you could do what are called slot reservations and say, okay, I'm going to buy $10,000 worth of slots a month, and I could run 24/7 in those slots, and I'm never going to pay more than that. So it helps with the total cost of ownership, and it gives it a little bit more predictability. As the centerpiece of Google Cloud's data analytics platform, BigQuery enables customers to break down their data silos. So that includes data that's stored in BigQuery's colossal storage, or in data lakes, or even in other clouds. We provide a fully managed entry point, not only into data integration, but preparation, ingestion, but to big data platform functionality like data science, BI, and data governance. Three key attributes to big data's value prop are reliability. I talked about that a little bit, but BigQuery provides the industry-leading SLA for high availability. Secondly is BigQuery is intelligent. So we build features into BigQuery to power machine learning and advanced analytics that customers typically have to deploy in third-party systems outside of the data warehouse itself. And finally, BigQuery is open. So that means that we're able to adapt to customer environments and to a wide variety of use cases. So we offer multiple points of integration with other tools and services. We have tight integration with the rest of the analytics products and services within Google Cloud Smart Analytics ecosystem. But like I said, we don't want to be a walled garden where everything has to be only Google Cloud products. So we offer various client connectors, JDBC, ODBC drivers that integrate BigQuery with all sorts of other third-party BI tools, analysis tools, anything that can connect up via client library or JDBC, ODBC. You could get data into and out of BigQuery with that. The second area of interoperability is database and storage federation. So database federation is the ability to query other data sources within BigQuery itself. So you could do that through various ways. You could do that through external tables in BigQuery. You could do that through external connections to things like Cloud SQL directly inside of BigQuery. We want to make it so that you don't have to log into various other systems to get the data that you're looking for. We want to make it so that BigQuery can be that centralized system that you could then log in one place, have the data governance and accountability, and get access to your data wherever it lives. Third, data ingestion is the foundation for analytics and machine learning. So whether you're building stream, batch, or unified pipelines, services like PubSub, which is our Kafka equivalent, they provide a simple and reliable staging location for all of your event data and on its journey towards processing, storing, and analysis. And our data transfer service connector can easily pull data from third-party sources as well. So one of the major advantages of BigQuery over our traditional data warehouse systems is its architecture. I harped on it that it's a fully managed data warehouse service, but this is what it looks like visually when you actually look at what this architecture is. So when you see the replicated distributed storage, that's Colossus, and you see it's probably like 10 nines of durability. So needless to say, if you put data into that storage system, it's not getting lost. The Dremel and the Borg clusters on there, you see there's those tens of thousands of servers. So that's another high availability feature that we have built in. And because it's a massively parallel system, that leads to itself the high availability. The petabit network as well helps in cutting down data transfer time between the actual storage system and the compute system. And because they're completely separated, there's no traditional sort of bottlenecks of having to scale up compute and storage at the same time. That was one of, like, in the Netezza world, that was one of the biggest issues that we had, is that customers would buy a box with maybe like 100 terabytes. They would have a certain SLA they would need to meet. And okay, they added more data. Storage was only like 20 or 30 terabytes, but their SLAs were suffering. So now, because everything is so tightly coupled, they had to buy a box that was twice the cost of that initial box, where with our architecture, because we have decoupled storage from compute, storage is separate. You could store from 0 to exabyte, we don't care. The compute is separate, and there's no direct correlation to the amount of storage that you have to the performance that you get. The only thing that affects performance is basically how you write your SQL and how much data you're trying to scan. So this is our managed storage layer. It's durable, persistent storage, optimized in a columnar format. It's the proprietary sister, so I mentioned it again. It's called Colossus. So this helps simplify your operations immensely, because you're not having to deal with worrying about partitioning, bringing up storage clusters, things of that nature. Data is compressed by default, is encrypted by default, and as you see here, it's replicated across zones in the actual region that you're running in. So if one zone goes down, your data is replicated somewhere else. So that's where we get those, I think it was like 10 nines worth of reliability for the storage. You're almost never going to have a situation where 3 separate data centers are going to all fail at the same exact time. Well, you might, but if that happens, I think your access to your data warehouse is going to be the least of your concerns.
It might become cut off easily.
Yeah. So some of the secret sauce of BigQuery is sits in between its storage and its compute layer, and that's what we call the in-memory shuffle. So we use remote memory shuffle to gain unprecedented query speed and performance on those big data sets. So this lets you query large data sets and get fast responses. Like I mentioned before, if a worker actually has an issue with query processing, another worker simply picks up that work that the previous one left off from the previous shuffle. So that gives you that reliability and resiliency. If something fails, it's not going to fail the whole query out. When the query actually completes, the results get written out to persistent storage and returned to the user. So this gives you two things. It lets you have a query cache, so the actual table gets printed out, the temporary table for that result gets printed out, so you could directly query that if you want to. But the simpler way of doing it is if you run that query again within 24 hours, BigQuery knows that it already has that data result set in that temporary table and goes directly to it. So that helps out for things like if you have daily reporting and that report never really changes, it doesn't have any like now functions or anything, it's always just a static report. You could run that thing at 12 o'clock in the morning. It might take an hour to run because it's such a huge report, but anybody hitting that same report, as long as that SQL query doesn't change, is going to get that result back in sub-second. So we're going to go a little bit into what projects are, data sets are. So a project is something that organizes all of your Google Cloud resources. In Google Cloud, a project is the top layer node of resource management. I'm going to focus a little bit more on what it means in BigQuery because I don't want to start confusing concepts. But a project, it consists of users, a set of APIs, of billing, of authentication, monitoring session for those APIs. So say, for instance, you have a project, all of your storage buckets, objects, user permissions for accessing them reside in a project itself. So you could have either one project or multiple projects and use them to organize your Google Cloud resources. Data sets are on the BigQuery level, so they're a top layer container that organizes and controls access to your tables and your views. I'm going to go into that a little bit deeper here in not this slide, but the next one. So we're going to talk a little bit about data sets themselves. So what the location of a data set is. There are various operations and properties that are associated with the resources that reside within a data set. So when you create a data set in BigQuery, you're selecting a geographical location of where you want your data to be stored. And there's two types of locations that you could pick. One of them is going to be a region. So it'll be something like US Central 1, which would be in Iowa. Or you could do multi-region. So for BigQuery multi-region, you would pick something like US. And what that'll do is that's actually going to copy those data sets across multiple regions within the US proper. Access control. So data set level IAM permissions determine the users, groups, and service accounts that are allowed to access the resources within a specific data set. So you could apply these IAM permissions a little bit more granularly if you need to. So you could grant permissions at the data set level or the table level and allow your users to access the underlying data. But many times we don't want to give them explicit access to table data. So we could use things like authorized views to share query results without having to basically give them access to all the data that resides in that table underneath. You could restrict that to certain columns as well. So there's all sorts of ways that we could slice and dice that stuff. Metadata management. So for metadata management, Google Cloud Data Catalog is a great option. What it is a fully managed and scalable data discovery and metadata management service. So it provides two main functions. There's searching for data entries, which you have access to. So like I mentioned, a catalog. It's basically almost like the way you could think about it is a Google search for your data. So as you provision out data to your end users, they could log into something like a data catalog and say, okay, I'm looking for the sales table. And as long as they have access to it, it'll show them, okay, these are the tables that have sales type data in them. So it makes their jobs a lot easier without having to say, okay, going to the DBA team and saying, hey, where do I look for sales data? Where do I look for item data? They could just go into the data catalog and look for that and find it. All right, so talking about the BigQuery resource model. So projects, they're the root namespace for objects. So they can contain multiple data sets, jobs, access control lists, and IAM roles. Like I mentioned before, they control users and user privileges. A good way to think about a project in a traditional data warehousing sense is a project would be equivalent to what a database is. So in like a traditional data warehouse where you have the ability to spin up multiple databases, that would be with us like a project. Below that would be a data set. So there's collections of related tables, views, together with labels and descriptions. They define the physical location. It's like I mentioned, US Central 1 or US multi-region. The way that you could think about of a data set in a traditional data warehousing sense is like a schema. So you could have one database, which would be a project for us. And then underneath that, you could have multiple schemas, which would be data sets. Jobs are what BigQuery runs on your behalf. So either being loading data, exporting data, copying data, or querying data, all jobs are executed asynchronously. And we've got some BigQuery table types as well. So a managed table basically just means the tables that exist within Google's Colossus storage system. Standard views, they're the same thing in any sort of database. They're basically just a virtual table that gets executed at runtime, something that you could use to sort of make your job of securing data a little bit easier. External tables, so those would be tables that are defined within BigQuery as a table, but they exist in something like Google's cloud storage or in separate OLTP databases as well. Materialized views, that's the one cool thing that I like most about BigQuery. They behave similar to what a materialized view behaves in traditional data warehousing. What that is you're taking a view and you're basically pre-computing things and storing it physically on disk. And then once you submit a query, the query optimizer looks and sees that, okay, this query that you're querying against this table, and there's a materialized view on that table. So it's going to say, does the materialized view satisfy this query quicker than going to the base table? If it does, then it'll go directly to the materialized view. So a use case for that is like if you have a fact table that's like 2,000 columns wide, but you're only really always going to be querying off of like 2 columns or so, you could build a materialized view and it'll cut down your time to actually get those results back much quicker. The one cool thing is that as data gets added to those base tables, that materialized view is being continually refreshed. And with us, the refreshing of that materialized view is a free operation. So other competitors that we have, they have materialized views. They behave the same way that our materialized views do, but there are a hidden cost behind that. So with us, you don't have to worry about, okay, I need to think about what data I really need in that materialized view and what tables they're going against, because I don't want to have a run up in cost because I have a 100 terabyte fact table that gets a terabyte added to it every day, and it then has to recompute that whole materialized view every single day. With us, you could do that because you're not paying for it. Some of the features that we have related to BigQuery storage. So all table modifications in BigQuery, including DML, queries that have destination tables, load jobs are ACID compliant. So when you're modifying a table, it doesn't require any downtime. We don't use any locks. What we're doing is we're assuming that multiple transactions can complete quickly enough without having to interfere with each other. So to ensure isolation, we use snapshot isolation. Storage layout. So traditional database systems lay out their data in a row-oriented format. That's great for OLTP type of systems where you're doing quick point lookups of single rows, or you're inserting and updating single rows constantly. But it tends to break down analytics workloads very quickly. So what we do is we store the data in a columnar format, and each column gets stored separately. And with analytics types of workloads, you're typically only really looking for certain subsets of a column. So like the fact table with the 2,000 columns in it. You're never really going to be querying all of those columns. You're mostly looking for aggregations of the columns themselves. So with us, because we're a columnar system, we're only taking the data out of those columns that you're looking for. And in a few slides going forward, I'll even show how we cut down further on the data that gets scanned. Data types. So we support a wide variety of data types. Each data type has several functions that you could use on it and operations that you could apply to them, stored procedures, and have things restricted to them. We have both structured and non-structured data types such as int, float, numeric, date, timestamp. In addition to these structured data types, we have the ability to ingest JSON as well. So that's one of the new previews that we've had recently, is being able to have a JSON dedicated column, which then you could query based off of a dot notation. I'm going to talk about partitioning and clustering in a few, but let's talk about loading data. So there's multiple ways that you could load data into BigQuery depending on the data sources, the data formats, load methods. So whether it be batch streaming or our data transfer service. When you ingest data into BigQuery, you're taking data from some source and converting it into BigQuery's internal storage format. You could ingest data using batch ingestion. So you could provide either data through Google Cloud Storage, so you could load it from a cloud bucket, or you could load it directly from an HTTP post request. We support several different file formats, so whether it be Avro, Parquet, CSV, JSON. When you load data, we could call this a load job in BigQuery, and load jobs are atomic. So all the data arrives all at once or not at all. If something were to fail within the load process of it before it gets into the storage, it just kills it. So you don't have to worry about reconciling differences in data inside the subsystem. Data also can be ingested a row at a time. So when you think about it in traditional OLAP systems, they're not really geared towards loading data one row at a time. But if you're using our streaming API, the storage API, that is something that could let you query the data directly from the streaming buffer as it's coming in versus waiting for a batched approach. Let's see what else. Data transfer service. So data transfer service allows you to load data from things like S3, from Redshift, AdWords, YouTube, Teradata. It's an easy way to get stuff over on a daily basis or on a one-time basis. I'm going to move a little bit quicker because I've got some, I don't want to spend too much time. One thing about load jobs is that if you're doing a batch load job into BigQuery, that is a free operation. You're not having to spin up compute for that. You're not spinning up a data warehouse to get that data loaded in. You're basically just loading that data, and it doesn't matter how much you load, if it's a gigabyte or if it's 100 terabytes. You're not charged for that load operation as well. So we provide data streaming as well. So this is for high volumes of unbounded and continuous arriving data, so near real-time analysis. One of the advantage of the storage rate API, which is what you would use for this real-time approach, is it supports exactly once delivery schematics through the streaming offsets. And then stream level transactions to the stream and commit data inside of a single transaction. It uses a buffer that retains recently inserted rows, and it's optimized for high throughput rates rather than columnar access. So a best practice here would be for data formats for loading data into BigQuery. Avro compressed is going to be the fastest. With it being a row-based format, we're going to be able to parallelize that as much as possible. Next would be Parquet. Parquet is columnar-based, so we actually do have to read the whole record. That can be parallelized as well. But then as we go down, CSV, JSON, the last two, CSV compressed and JSON compressed, are going to be slower because we're not able to decompress that on the fly. So we're going to have to, we're not going to be able to take advantage of parallelization through that. So ELT versus ETL. We want to do ELT, or extract, load, and transform, as a best practice in BigQuery. What you should be doing is you should be having, say, like a raw table where you load all your data into, and then you could use the power of BigQuery's system to actually transform that data. So that's going to, one, save you on time, and two, save you on cost. The traditional ETL tools, they're not really that very high horsepower. So by the time the transformations happen and the actual load gets into the system, you could have loaded that data in this raw form and transformed it directly through BigQuery. Partitioning. So this is one of the ways that you can get performance out of your system. So there's a few ways that you could actually partition the data. And what partitioning does is it lays the data out on disk as close to possible in a certain format. So ingestion time is one of the ways that you could do it. On a timestamp, that's another way you could do it. A good use case for this is if you have a table where, say, like a sales table, and your analysts are always looking at, okay, give me the last 3 months of data of sales. If you have a fact table that has 5-10 years worth of data in it, and you don't partition the data, it's going to have to scan that whole table, which is going to take longer than it would if you partitioned it. If you partitioned it, like you see on these slides here, that green one is 2018, March the 2nd. If your analysts look for that specific date, they're not going to scan 100 terabytes. They're only going to scan of, that might be, a few kilobytes or so. So that query is going to come back within sub-second versus a minute or two. Further optimization can be done by clustering. So once you partition by, say, that date, now you could cluster based off of something like the tags. So then that same example of 2018, March 2nd, your queries are looking for that date, but they're also looking for tags as well. So that would be a good clustering key, because then the data for the date is going to be in one partition, and then the actual clustering key is going to be put together as close as possible inside of that partition. So not only are you cutting down on scanning the whole table. Now you're cutting down on scanning the partition itself. I'm going to go past this because this is stuff that I've really already talked about, query processing. So there's several ways that you could actually run queries in BigQuery. The first one is using the BigQuery UI. So you see to the left here, we have our project, BigQuery public data. Underneath that, we have our data sets. These ones happen to be actually the public data sets that we have available to us. So you could write your query in the top right here, which is a standard sort of SQL Workbench query tool, and then have the results populated through the bottom query results pane that you have there. One of the things with this approach is that if you're using the on-demand model where you're paying for the actual data that you scan, this will say, like right here, it might be a little bit hard to see, but it says this query is going to process 72.47 gigabytes when run. So that will give you a sense before you actually run the query of what the estimated cost is going to be. Because for us, you're paying for storage separately, and then you're paying for the actual data that gets scanned. So for something like this, if you're writing something out and all of a sudden you see it's going to scan 100 terabytes, that'll give you a quick heads up to say, hey, maybe I shouldn't do select star on this. Maybe I should trim the columns a little bit here. We could query via CLI tool. I know that when I was in the TISA, that NZ-SQL was a tool that I used all the time because I was able to do my queries quickly without having to use a UI. And this will let you do things like scripting out queries as well. You install the Python-based CLI package on your laptop or within the Cloud Console itself, and you could write queries directly in the CLI tool. We've got Python client libraries. So if you're familiar with Python, you could use those client libraries to directly access the data that's in BigQuery. So if you have Jupyter Notebooks, this is a handy way of getting the data directly out of it. I mentioned before, any sort of JDBC, ODBC tool, you could run and get the data directly out of BigQuery through that. Curl post commands, you could do the same thing as well. And then the kinds of SQL that we have, this is pretty standard stuff, so I'm not really going to bore you with this. Persistent UDFs, so we let you create SQL and JavaScript functions that you could reuse across your queries and share with others. So you could do things like automate certain tasks, save time, and have more consistency and scalability. Stored procedures, same thing like in any other sort of data warehouse environment, you could write stored procedures. And table value functions are user-defined functions that return a table itself. So if you have the need to have that sort of approach where a function returns a table, this will do it for you. Okay, I mentioned query execution. So query execution is dynamic. So with us, the query plan doesn't have the need to stay the same from the very beginning of the plan to the end of the plan. What that means is that as the query is being executed, the optimizer is continuously looking at improvements. And if it sees for some reason that the initial path that it wanted to take isn't going to give the results back quick enough, it can actually change path during the query execution itself. And if you see that happen in your query execution plans, it'll be something called a repartition stage. So some of the best practices with us, the first terabyte of data that you query a month is free. So if you're just trying to play with BigQuery, you could be safe that as long as you're underneath that terabyte a month, that's perfectly fine. I mentioned before, partitioning and clustering your tables is going to cut down on a lot of data scanning on the on-demand model. And then, avoiding SQL plan, anti-SQL patterns like Cartesian joins, self-joins, things of that nature. Nothing too revolutionary. The data transfer service. I sort of briefly mentioned that, federated queries, so I'm not going to really go into that too much. GIS, we have the ability to query GIS data directly inside of the database. So when if you have use cases, if you're looking for certain polygons, certain geographic types, this will be able to run those functions directly inside the database. BigQuery BI engine, I mentioned that before as well. It's a very low latency, high speed service that you could use for high concurrency reporting type workloads. And BI, we have BI built in, so you could use things like connected sheets for people that aren't really familiar with data warehousing with SQL. You could have them connect up the data to a Google Sheet, which is the same thing as an Excel sheet for analysts that are familiar with that format. You could use built-in Looker Studio, which is our free BI tool, to do some quick reporting based off of BigQuery. Or if your needs get a little bit deeper and have a little bit more enterprise-grade need, you could use Looker and LookML to build a semantic layer on top of your data and then have your analysts be able to build reporting based off of that in a self-service model. All right, with that, I'm going to hand it off to the Faraday team. I'll let them introduce themselves.
Thanks, Chris, for the overview on BigQuery. Before we get started, I'm going to have everyone just like stand up, reach for the sky. You got like 15 seconds, 20 seconds, stretch out if you want a little bit. We're just going to be here for 15, 20 minutes of talking about, yeah, there you go. Perfect. Okay. So my name is Hannah, and this is...
I'm Dave Shirley.
And I'm a platform engineer at Faraday, and Dave is a data scientist. And we're going to spend the next 15 to 20 minutes talking about building a predictions infrastructure for U.S. consumer behavior on BigQuery ML, and kind of our experience using BigQuery and BigQuery ML to power our business. Oh, sorry. There we go. So what is Faraday? Faraday is a prediction platform for brands. Like I said, we're built on top of BigQuery and BigQuery ML. We've got hundreds of brands with billions of rows of customer data and trillions of predictions. And through the Faraday platform, those billions of rows of customer data all pass through BigQuery at one point or another. And those trillions of predictions, they can fall into one of three different categories. We can be talking about propensity predictions, such as propensity to buy or convert from a lead to a customer. We can be talking about persona predictions, like used to sending personalized emails. Or we can be talking about forecasting predictions, like predicting spending of a certain customer over the next 3 months. And these predictions, they're not just based on client data, but Faraday also brings this kind of rich identity graph to the table. We've got 100% permissioned opt-in data, cookie-free, it's never scraped data that we source from like the Epsilons, the vendors of the world. And we've got information on kind of the 270 million adults and kind of 400 different attributes across that population. And they can be demographic information, location information, where are they, family, property, financial information, even stuff like, do they have hobbies? Do they like to garden? Do they have a dog? Like, have their kids go, stuff like that. And so it really helps amplify the predictions that we can make, not only operating on the client's data. And so this is a big picture overview of data flow through Faraday. From a client's perspective, they're going to connect their data. They can upload a CSV file of, say, their orders or their customers' data, or they can connect directly to a data warehouse or any other part of their stack. Then they're going to define their objectives. They're going to say what they want to predict, and they're going to do this inside of our self-service app. And then finally, they can deploy their predictions once they're done. And this is pushing their predictions back to really anywhere in their stack to make their existing tools work smarter for them. And along the way, Faraday is using BigQuery and BigQuery ML to power these client goals. So after they connect their data, Faraday is going to automatically identify people who are in that client's data set with our identity graph. And then after the objectives are defined, Faraday is going to automatically build and then validate and then also keep up to date the models that we have for them that power these predictions so that as new data is pushed in, new predictions are pushed out. And so the thing about this is this embeds predictions within existing tools that clients are already using. And so each of these use cases on the screen represents, a different scenario. Say on the left, a client comes in and they want to predict their lead scores and deploy them to Salesforce. So like our data flow would be, we could sync their customer data from BigQuery. Say that's where their data warehouse is. Then we could create a conversion propensity model and score all of their incoming leads and push them back to Salesforce every single hour. And in this scenario, it would enable them to respond in real time to the leads that are highest priority. Say they don't have the resources to respond to every single lead. They don't want to spend it on people who maybe don't have the high likelihood of converting. So it allows them to prioritize their leads in real time. And say that second case that's listed on the screen, we want to predict our likelihood to buy and deploy it to Facebook. Say in this case, a customer has their data in S3, right? We'd sync their data from S3, and we could create a purchase propensity model. And then we could score all US adults with that model and deploy to Facebook as a custom audience, allowing the customer to target people who have the highest propensity to purchase their product. And then in the third case, we could also predict personas and deploy them to Klaviyo. So we could, sync in their customer data and make persona predictions and assign it to all customers that are incoming and then push that data back out to Klaviyo so that they can send kind of more personalized emails. And no matter where client data originates, we're going to bring it into BigQuery using all the tools that GCP provides, data flow, BigQuery, BigQuery ML. Everything flows seamlessly and really scales flawlessly, and we'll touch more on this in a minute. And so, like I said, using these tools, GCP is able to make predictions that allow our users to make operational decisions and integrate them into their automated processes that they already have in place and see benefits where it matters most to them. So this is an architecture diagram, and it's got a lot of arrows. But basically, the gist is that Faraday is data source agnostic. No matter what, like I said, we're going to bring it into BigQuery. And that middle box there, that's the GCP platform, and inside that is Faraday. And you'll see that we actually use a number of Google and GCP services to power Faraday itself. This touches on something that Chris said earlier, basically that once you get the data in, you can decrease your costs, you can have more scalability, more stability, more speed, and you can just move it around in the Google Cloud Platform. And so, yeah, once we can pull it in from any source and then operate in the Google Cloud Platform and then push it back out to where the client needs. All right, so let's look at some really specific use cases and how we're using modeling. So, one second. Say you want to increase your conversion by sending more relevant emails. In Faraday land, we call this a persona set. And in the app, they would be guided to, say, upload their leads data or their customer data and guided through creating this persona set. And personas are distinct clusters around shared traits that are useful in understanding who their audience is and how to better connect with them. And these predictions, like I said, can be plugged back into their existing stack to send more targeted marketing emails. And so how this works is, like I said, they're going to create their persona set. But behind the scenes, Faraday brings their data onto the Google Cloud Platform if it's not already there, and BigQuery ML makes predictions. So I'm going to hand it over to Dave, and he's going to talk about the modeling that we're doing here.
Okay, so you can see in step 3 there, the create model statement. That is a pure SQL statement where we're specifying where we want the model to go, so some options for that model, and we'll specify a source, which is the training data that we're going to use for the model. And we'll go through a couple of different examples, and you'll see that they're pretty much all exactly the same, just with some different options. The difference is mostly going to be in the training data sets that we're building. This particular one is a k-means clustering. So we're going to be building a training data set that doesn't have a label or a continuous output variable. It's just going to be breaking things up into clusters.
The second case that we'll talk about is lead scoring. We touched on this earlier. Say you want to know the likelihood of fresh leads eventually becoming customers so you can, respond to them in priority. And in Faraday land, we call this an outcome. What's the likelihood that this group of people that I identify as leads becomes a part of this group of people that I identify as customers? And so in the app, you'll be guided through creating an outcome. And then behind the scenes, Faraday brings your data onto the Google Cloud Platform, and BigQuery ML is going to make predictions again. And so, Dave.
Yep. So this time we've got a binary prediction. Someone either has the action that we want them to take or doesn't have that action. So we can put together a training data set which has people labeled as good or bad. So then that goes into the training data set. And we run a very similar BQ ML create model statement. All this is in SQL. We were creating the training data set in SQL. We're creating the model in SQL. Very, very straightforward, no transitions into a different language, no complex orchestration. It just works. Pretty low drama.
We love low drama. And the last case we're going to talk about is spend forecasting. You want to know how much an individual will spend with them. And so Faraday land, again, we have a name for this. We call it a forecast. And so in that app, you would create a forecast, and then Faraday will bring your data onto the Google Cloud Platform, and BigQuery ML is going to make predictions. So take it away, Dave.
I think you're spotting the trend, right? So exact same thing from a Google modeling perspective. The difference is that you're going to be putting together a slightly different training data set. So for the binary classifier, you have a good versus bad label. Here we're going to have some kind of numeric column, which is what the value we're looking to get predicted is. So spend or whatever it happens to be as a continuous outcome.
Nice. And so all those things that we talked about, those are different types of modeling. And so the step after modeling is scoring. Now that we've created the model, who do we want to apply it to? And so in Faraday land, we call this a pipeline. And so you choose what kinds of models, like the models I all just made, what am I going to use them for? And who do I want to apply them to? What's the population that I'm interested in? And so this is where the scoring comes in.
So again, we're putting together a data set, but rather than having a label or an outcome, this is just the features part of that data set. We can basically reuse most of the SQL, and now we're running a ml.predict on the model that we've previously created.
And once that is complete, we have these predictions available to us, easily accessible, that we can make available, leave them in BigQuery, or we can push to a CSV, or really anywhere back into the client's data stack. Again, putting them somewhere that they can use them to power their business decisions. And as a kind of fun plug, all of these screens that I've showed, I talk about, you can configure this in the app. We recently also launched an API product. So that's another way that clients are interacting with Faraday through this API that we've developed. I think a really awesome thing about BigQuery ML is it's made these predictions accessible, but we've also had many years developing this predictions infrastructure. And so this is in place through our API. So that's something that we're pretty excited about. All right, so next we're going to talk about some roses and thorns about working with BigQuery and BigQuery ML, kind of in production in a production environment. So our rose number one is zero ETL, and Chris kind of touched on this a little bit. We've been around for a while and haven't always been using BigQuery ML. And our previous system required ETL. It required that we moved the data to the place that we needed to make the predictions every single time. And we had a tool for this. It was written in Rust. It was solid. It was 99.9% reliable, which meant that it failed all of the time. It was like a daily thing to check, like, okay, let me just go retry that thing. We had very robust retry logic automatically, like manually. It was a deal. And in this aspect, BigQuery ML is really a dream. There's zero ETL once the data is in its place. So in this case, like data locality, it's not just this like random buzzword. It really helps us operate in a truly like in a more stable way and also in a faster way. And our second thing, again, Chris touched on this excellently, is the serverless infrastructure. So our previous ML system really couldn't handle volume well. In 2019, we had about 98 billion scores at our max throughput. And this, again, had heavy duty retry logic. It was kind of this question of like, how are the clusters doing? Is everything okay over there? Do we need to scale it back up? Is something stuck? Unknown. And again, here, I'm going to say that BigQuery ML is a dream in this aspect. In the first half of 2022, we've pushed over 1 trillion scores through BigQuery ML with no retry logic, which is baffling to me. It's amazing. It really makes it so much easier for our engineers to focus on what types of models do they want to configure? How do we want to think about other things? Like, how do we want to think about bias in models? How do we want to think about, are these models cheating? Are they configured correctly? It allows our engineers to think about those things and just trust that the modeling, it's going to come through. And our rose number 3 is a responsive product team. For example, we had this scenario where, you know, our clients say they were geographically located in one area and they wanted to grow out of that area. But their geography was heavily weighted in their prediction. So they were getting a higher likelihood of people showing up in their predictions in the area they already were. And so we wanted to de-weight that. And BigQuery ML didn't support instance weighting. In April of 2022, Faraday talked to the BigQuery ML product team about this. And in August of 2022, the XG Boost instance weight feature was released into preview. And we've been able to play with that and use it and like basically implement geonormalization through this product that they put out. Did I get out? Is there anything else to say about that one?
Yeah, I mean, the reason for having this is if you don't do this and say you've got a real big geographic imbalance, you'll end up sort of predicting things that are much more to do with, like, you know, housing. You'll be predicting like what state people are in rather than like whether they're going to become a customer or not. Yeah, so you don't really want that. We're also probably going to be using this feature to help with some bias mitigation work. Bias mitigation, you can do like pre-modeling and post-modeling mitigation, but this will probably help with some of the pre-modeling mitigation.
All right, so now we get into some questionable rose thorns, and I'm going to hand it off to Dave, and he's going to talk about some of the workarounds that we've done with BigQuery ML.
Sure. So BigQuery ML is like pretty straightforward to use. It comes with various features which are pretty well documented. There's a bunch of things like you saw the ml.predict function and the create models. You can look at features. There's various things that you can do. You don't get the complete set of feature parity with, say, a Python typical developer environment. So there's a bunch of things that you can't do. But, you know, a model doesn't have to be perfect. A model is as good as it's, you know, what it's used for. If it increases if it provides value to the person who's using it, then it's great. And these are so easy to set up that you don't have a bunch of other costs associated with the setup of the models. So, and you can get quite creative with these. We've been doing things with feature selection. There are some feature selection related things, like you can have, you know, L1, L2 penalization. You know, we're doing various things where we're fitting multiple intermediate models and looking at the feature importances, and then going and fitting more models and looking at properties of how these were fitting. We've got some dynamic scoring features where, depending on like where in a customer's tenure with a client they happen to be, different features are going to be coming up as important, and so we can fit different models and use different models at different points in time there. We've got some backtesting work where we're going and reevaluating models at various different points. There's some cross-validation that comes out of the box. We're going a little beyond that because it allows us to save the results and reuse those a bit better for our reporting. You can, you don't have to worry too much about the orchestration side of things. You just write some SQL and, our SQL gets called out from the Python SDK. So we do a little bit of orchestration in Python, but it's very lightweight. We don't have to worry about any of the scaling side of things. So we're able to actually get quite creative within this framework, even though it isn't like a traditional data science kind of platform. So,
I'll take it. All right, and so we'll close up on some thorns. So I'm going to just touch briefly, like right now we don't have survival modeling and no dedicated LTV. But again, we can have these workarounds like Dave talked about. And the thing that I want to talk about last is there's this slot reservations learning curve that we kind of went through. Eventually we ended up kind of creating a separate project for our ML queries to be run in, and this works for us. It's an on-demand one. This works for us because our training is really fast. But something that's really great about this slot reservation system is at this point right now, we are currently doing some optimization on how our jobs are running, when we're choosing to run them, and how much they're costing. In the analytics that BigQuery is able to provide back about each job, how many slots it's using, how much it's going to cost, how much data it's going to process, enables us to kind of align our business priorities with our business costs in a way that kind of our previous system where, everything's just running on this cluster. It's not split out by job. It's not split out by resource. It's not split out by actual client who's using it. It's kind of like, here's your bill at the end of the month. Your cluster was running fine, sort of, to now where it's like, this job costs this much. And this client who, maybe this client who has a lot of data, maybe you don't need to be refreshing it so much because this is how much it costs to run their predictions. So we can really, with these slot reservations and with the information that we get about how jobs run and how they consume slots, we're able to align our business and how we run it and how we run our jobs, how we query them up with kind of how much they're actually costing in real time. And so in conclusion, the Google Cloud Platform is a great place to do ML. Like Dave mentioned, it really gives this great interface. It's just in SQL. It gives this great interface for data science to be able to focus on the actual modeling part, what kind of models they want to do, how do they want to configure them, instead of thinking about the extras, thinking about the setup, thinking about the scaling, the scalability, and everything like that. It enables continuous intelligence, and Faraday is kind of integrating with client data to do that, built on top of the Google Cloud Platform. Thanks.
Thanks, guys. So we're gonna take a quick 5 to 10 minute break because I know it's been a long while, so we want to get up and if we have any refreshments or anything else. And then let's say 6:50, we'll come back and we'll do the fireside chat. So Sanjay will lead that. He'll have some questions for the Faraday team. And once he's done with his questions, we'll open up the floor for questions from the audience. So 10 minutes, come back at 6:50. I think I have to stop. Stop presenting. All right, so you're going to see yourself, which is going to be a little bit.
Right. Just don't look up.
At least you'll know you're in the right.
Oh, your posture is really bad. You should work on that.
Right, I think we get started. Let me. This over here, when you're done, your questions that people can come up and ask.
I mean, I should walk around, that's fine. I don't know if you would want to come up.
Okay, sure. All right, yeah.
It's a small room. People can shout.
Okay, okay, cool.
All right, we have everybody in? I think so. Okay, perfect. Thank you all for coming today, first of all, and sticking around. I know we're a few minutes over, but we want to get, after hearing a great presentation, you want to talk to the people who presented. You want to ask them questions. So we're going to stick around for a few more minutes, and I won't take too much of the time. I'll have maybe one starter question for Hannah and Dave, and then I'll open it up for you guys to ask your questions. First of all, thank you for your time. I know you had a drive coming down here, so appreciated your time and coming here as well. We heard some great use cases that Faraday is solving for. We went through some of the good things you're experiencing with BQML, some of the challenges you overcame, everything. What's the future look like? Like, what do you see going forward? Maybe some exciting things that Faraday is launching, things that you're looking forward to addressing in the market. It'd be good for everybody to hear what's coming next.
Yeah, for sure. And thanks for hosting this and this Q&A. So a couple of things. One that I touched on in the presentation, we've had some work going on with kind of bias detection and reporting. And we have some ongoing work around bias mitigation that we're really excited about. I think there are these well-founded questions about kind of AI, about ML, about like, what are we still going to, like, what's still being propagated by this? Like, how much bias is in here and how much should we be concerned about it? Like, can we just like trust these models wholesale? Like what's going on? And so we're really excited about the bias mitigation tools that we are currently working on. Additionally, still kind of plugging our API, we're excited to have kind of clients building their products on top of the Faraday API. Which is really exciting. It lets them kind of focus on their area of expertise while consuming our predictions infrastructure. And then finally, our something that's on our roadmap and is kind of ongoing, is kind of at the cusp right now or just happened, is this kind of self-service experience for kind of Faraday's history. We've been this kind of in more of a, not a consulting basis, but a lot more of the power was in Faraday's hands. Faraday was operated by Faraday employees, and now it's getting to this point, and it's at this point, right, where a user can log into the app and they could do everything themselves. So this is just like a really exciting place to be at. Anything you want to add?
Sure. So one of the things we've been doing at Faraday is building out ways to make better and better models, and expanding our product line, and like doing more and more work behind the scenes. And with that comes increased costs. We've started to really look at trying to pare back some of the things that we're doing. So for instance, we maybe build two different models and then look to see which one wins and then deliver to the client the best one. And we're starting to spend a bit of time looking at reporting internally on how these things are doing, and reducing some of our costs by doing less work. So there's a bunch of handy tools to do with reporting that we're using to help with that.
Yeah, that's great. I'll probably make a quick comment, and then if anybody who wants to ask questions can raise their hands. It's one good thing to notice with the response that both Hannah and you provided was one, addressing both the things, right? One, looking at the industry and the trends and what might come up in discussion. We have product features coming up, and that's also technically keeping the product ready to be able to meet those needs. So there are efforts being made on both ends. I'd love to hear any questions. I'm happy to pass the mic along if people have questions.
Thanks. So we've heard a lot about the benefits of BQ and how you utilize it. It'd be interesting to hear what features you wish BQ had going forward that would enable certain business case issues that you're trying to solve right now. Are there any features that you wish BQ had to make your work life easier?
You have a thought there?
Okay, so I could talk about some of the gaps in modeling. One of the other things that comes up is to do with queries running out of certain resource types. So if you try and do an order by in a ridiculously large table, it's going to break. So there's those couple of things. Do you want me to go into detail on like any of those?
I mean, it's up to you, man.
If
you want to vent, like this is it's an open forum.
Everything's perfect. A+, you guys.
Let the people know.
So we have a couple of modeling types that, if we want to run like survival models, we can't do on BQML, but we can work around that. You can do binary classifiers for like, is the person survival is like alive or dead type. So you can use a binary classifier. It also tells you like the time to that event. So you can use a regression for that. So there's workarounds for things. I think lifetime value, there are some specialist models that you can run where there's less of an equivalent thing off the shelf. But in general, we can make things work. And like I said, there's no such thing as a perfect model, just some models are more useful than others.
Yeah, and I mean, to touch on what Dave said, where we sometimes have this this case where a query is going to run out of resources. And, the most recent time that I ran into this was I was partitioning over a massive table in an order, which is obviously good. Like, I was trying to avoid doing a graph walk. And so was sending this huge table through this query. And at some point you have to wonder okay, BigQuery is probably not broken or lacking resources. I'm just using it incorrectly, right? Like it's not supposed to be able to partition this table over a single node. Like it's just not, it's not realistic. So, sometimes we push it up against those things, but also at the same time, you can understand, this actually isn't the best. This actually isn't the best approach. Like I shouldn't be attempting to circumvent, doing some graph walking by trying to do this partition thing. So maybe a different approach is better. So
Sounds good. And any other questions? Hey, Dave.
Wow. As you guys were describing BigQuery ML, I felt like it was like a bit of a cliff, right? Like David showed the slides on like some of the maybe crazy things he does, so he can actually model do his models in BigQuery ML. And if you can't do it in BigQuery ML, I don't know, Hannah's writing ETL and Rust for some reason. But like, what do you do when it doesn't work out in BigQuery ML? And what's your approach towards making your more custom and maybe like a Python-based model feel more like BigQuery ML in terms of like auto deploy, auto scale, auto everything?
I mean, I think at this point we've implemented the workarounds. We migrated onto BigQuery ML off of a different modeling platform, and we've thrown out ideas around like how would we implement these custom models, running them in house. But we've run with the workarounds for now. I don't know. Do you want to say anything about this?
Yeah, I mean, the other thing is, ask Google folks nicely and hope that they develop it, because, I mean, it's worked out for us, and it saves us a whole bunch of time and effort. I mean, we're not short of things to do, so we can stick with some of the existing products that we've got and spend more time working on like the ethical AI type things, with the bias and working on improvements to feature engineering and stuff to do with the huge, maybe new transformations within this huge trove of data that we've got, which is part of Faraday's value proposition. So like we can look to some of the core things that we do well, and just work on those and wait for some of the other things to come along. That said, we do have, is it Falconary? We've got, I think it might be an in-house chunk of software for, we use it for geocoding and a few other things where you want like a super high parallel custom workflow, where we can like spin up our own little clusters of jobs and really do a whole bunch of work in parallel. But if we're going to do that, we've got to think about efficiency and how you structure it and all that kind of stuff. And that's what you guys are doing. So we can let you guys do what you do well.
Nice. I mean, having a great product team and the support team always helps. But looking at back a few months and years, maybe 2 years with BigQuery for you guys, I believe, what would you recommend somebody who's just starting off with? Any learnings that have stood out for you? Anything that somebody who's beginning out of their journey should know about?
Want me to start? Read the docs. The docs are great. It's easy to jump in and be like, I know SQL. Let me just start going. The docs are excellent. So I would recommend starting there. Obviously, that's a very basic answer to give. In terms of, kind of unlocking what makes BigQuery and working with BigQuery ML, a really great experience. I have to go back to reading the docs. Like I've discovered it, like some of the partitioning stuff and clustering stuff and even more advanced things that, Chris talked about. Some of them, it's kind of shown up. It's like, I don't quite understand. Like, I'm sure BigQuery has a way to do this. I just don't know what it is because I've never needed it before. And so just looking through and saying, what do the docs say? What's the recommended workflow can go a very long way. But also, BigQuery has a whole bunch of test data sets that can be really easy to jump in and start working with, start getting reports out of, start using. And so even then, you're skipping the step of having to upload your own data. You can start playing with it immediately with these public data sets.
So BigQuery is pretty quick, but it's really good for like larger queries. So don't forget about other things like Bigtable, which we use for, I think that's the back end to the API, right? We're using that where we want to have like a snappy response to something. So, we build things in BigQuery and then we push them into Bigtable. So there's that. There's also various like per project quotas, which are various soft limits, and you need to be aware of those as you start scaling. We've run into some of the issues with things like working out where to send longer jobs versus jobs that require huge numbers of slots, and trying to sort of triage those. If you're trying to run a job interactively, there's I think a limit of 100 queries that you can run interactively concurrently, which is great if they're short because they'll probably complete quickly. But if you try and run a bunch of queries that are going to take a couple of hours each, you're going to hit that limit of 100 and you're going to start getting errors. So there are various limitations that you run into as you scale that if you haven't read the docs, you might get caught by surprise by.
Great advice.
Sorry. So you mentioned that you have a new API and customers using it. Are these just paying customers so they get to use the API as much as they want, no matter how much they spend with it? Or do you have some concerns that they could use the API to spend a lot of money? And if you do, how do you figure out how much each one is spending?
Yeah, and so with the API, typically we've seen so far that customers who have been our customers for a while and they interact with the app, they're not the ones who are using the API. We have new clients coming in who want to build their products on top of the API. And so they go through a different pricing structure. Soon it's going to apply to everyone, but at the moment, or it's going to apply to everyone coming in, and then they can get on kind of a committed plan if they'd like. But the pricing structure is based on predictions per day. So it's really tied, their predictions are tied to their usage, and they pay for them when they get predictions out. So they're not paying to bring their data into BigQuery. They're not paying to, whatever. They're paying for when the predictions come out. So that's how we're handling payment that way. Another form of the API, like Dave says, we kind of have two parallel tracks going on. With this is kind of scores that we've had for a long time. We've had this API product for a while where we'll create scores and then we'll cache them to Bigtable and serve them up over an API in real time so people can, clients can hit that API to power their product. But yeah, this new API product is a separate pricing structure, and it's limited. They're paying based on their predictions.
And they just don't have the ability to spend way too much money because you're not giving it to them.
Yeah, so they get to see, they can get kind of like, this is how much this prediction will cost. Do you want to make a deployment now? And so they get charged based on the predictions in the deployment. And when they send the deployment, that's the cue. Like, yep, I know it.
So I have a very basic question, naive question. So I come from a local biotech company, and I've been doing this for over 15 years. So trying to wrap my head around BigQuery. So how would you use if at this moment BigQuery wasn't around, or what's the next thing that comes close? That's one question, and I have another for everyone.
Yeah. So before we in another iteration of this presentation, there's a snapshot of our principal engineer, and it's from 2018. And it's when he first kind of discovers BigQuery, and he's just playing with it. And he's like, this makes our 200 copies of Postgres running look like a toy. So we've run queries kind of across distributed architectures. We're on kind of a distributed Postgres, and we're operating that way. And so, but we had a lot of problems with it. And so that's why we're thrilled to move to BigQuery. So there are other solutions, but yeah, it's above it. It's great.
So, thank you. Second question is that's for everyone, really. In most of the presentation Chris gave, and to my knowledge so far, there's disproportionate amount of mention of BigQuery versus GCP. So can one use BigQuery in a standalone mode without subscribing to the GCP ecosystem? This is another naive question for everyone.
I don't think so.
No, I mean, in order to spin up BigQuery and use it, you do have to spin up a GCP instance. I mean, that's the same with any sort of hyperscaler. So whether you use AWS or Azure, you do have to actually spin up an instance of AWS or Azure, have a billing account, things of that nature. There's ways of trying out BigQuery, using for GCP, you could have a trial account and get $300 worth of GCP credits. But yes, you do actually have to have an account. You don't have to have a organization per se, because when you have an enterprise and you're actually building a GCP platform for that enterprise, you build an organization, and then underneath that, you would then have projects and billing accounts and things of that nature. You can run without an organization, So it's not like you have to build out a complex structure, but long-winded way of saying you do need to have a GCP account to use just BigQuery.
Yeah, thank you.
BigQuery does have a feature of being able to access data outside of Google Cloud as well. BigQuery you need to access data that is outside of Google Cloud and still interact with that data. But to use that product itself, you have to be on the platform.
Okay, so that means there are underlying resources that I will be using. Of course, I need, a GCP account, but there will be,
Correct. So you can
ecosystem
access-
of resources.
Through BigQuery, you could access data which you have somewhere else.
Gotcha,
This
okay.
is,
Yeah. Interesting. Yeah, thank you. You mentioned interoperability, so that's why, it got me thinking. So can I bring my, AWS data into
You could
BigQuery?
be your window to access data, and you could still run your queries, but the data can be somewhere else.
Gotcha. Thank you.
I just wanted to give an example of using BigQuery on data that comes from outside. We had a LIMS system on-prem, which was supported only in AWS cloud by the vendor. So we set up an environment there, our LIMS system's there, its Oracle database is there, but we replicate, and not exactly replicate, but we do take every modification that goes into that Oracle database and stream it over to BigQuery and maintain a BigQuery data set for our downstream processing.
Any other questions?
Yeah, I was curious for model deployment and version control. Do you guys do any sort of CI/CD for your model code? Do you, how many models do you deploy to production, let's say per month, ballpark? And how does that work?
Oh, I didn't even estimate.
I'm not sure about exact numbers. I mean, we build, like a lot of the times we'll have maybe 10 or 20 models building at a time, like quite a lot of the time in our model build project. But in general, we try and, the models that we're building are reasonable to keep around for a good chunk of time. They're built using a reasonable historic period of data, and the expectation is that they're not, the ground truths that sort of sit inside the model aren't going to have changed substantially. So we maybe refresh models like quarterly or something like that. Now, in terms of like version control, like the models you're naming like any kind of table. So you saw in the screenshots, you've got the project, and then you can have like sort of a folder structure there. We have like a folder that's models, and then we name the models according to the resource that we're dealing with. So internally, we have we have a Postgres database that keeps track of like a lot of the state of our system, and so we create a new row in that gets an ID. That ID goes into the name of the thing. So and then like the various bits of metadata on the Postgres row will tell you like when it was created and all that sort of stuff. So we've got this internal tracking system that then points out to like where data is sitting in various different points, and each time something runs, we refresh like what the latest outputs are for a given thing. And does that answer your question?
It does. And then are you using Git or something to version control the SQL or to create model statements and things like that?
So
I can do.
So I mean, the different types of model generations, that stays pretty stable, but then say we move in, we tweak it, and we make a different model type, that gets a different name. So like Dave said, for any given set, we might generate 8 different models, or maybe not that many, right? For a given set of data. More than 8. Okay. We're going to generate a bunch of different models and pick the best one. And so so for each different configuration of model, when that changes, right, we're just going to make it a new modeling type, a different strategy for that, and then that's kind of how our version control works. So we're not tweaking the model configuration in line. We're just making a different model type.
Perfect. Thank you.
You said that you chose to use Bigtable to give the clients their scores. What kind of decision made you not stay in BigQuery for part of what you're doing? And when would you consider something like that? What made you consider that? Is Bigtable store something differently, or?
Yeah, so Bigtable, we cache scores to Bigtable for certain clients who want to access and want to stream data like over an API kind of in real time, as opposed to us pushing scores back out to their stack. They're gonna hit the API, and Bigtable just has lower latency. It's faster, and that's why we made that decision. Anything else on that?
It's faster.
Yeah. So the say if we're like generating, if we wanted to know, say somebody calls into a call center, and we want to know what the chances are that they're going to be a really good customer. The person in the call center would want to be able to query that like straight away and get a prediction score back. So we're going to do some of that work up front. So we're going to score everybody in the US. This is anybody that could reasonably be queried. So we'll use like an ML predict, pump that into a regular BigQuery table. And then the results of that BigQuery table then get shoved into Bigtable. And so then when you want to retrieve a single row from that, you're not having to query a table that has 270 million rows and is stored as a column store. I think, is Bigtable a row store? It's still column, but it's a lot quicker. Rather than it taking somewhere maybe a few seconds, it's in the millisecond range, if I remember rightly.
So yeah, I mean, it's per use case, depending on that one use case, which is better served from Bigtable, is what made you take the decision. Makes sense. All right, I think we're about, perfect.
Yeah, just a question about retraining the model. So you spoke about predictions on like new data, you can do like real-time predictions. How about the approach to retraining on new data? So do you use previously learned knowledge or stock Google GCP models?
So depending on the type of model, the most of the models that we're working with, you provide them with a features table, and then that's used to produce the predictions. So if you're working with certain model types, like I think ARIMA will give you, you just get a single time series out of the model. You can't like request new people's data in the same way. Then people are going and retraining the models every hour. But for our purposes, as long as we have seen similar people and similar behaviors in the training data set, maybe in the last 3 years, people have exhibited a particular behavior, then the models will be able to pick up on that and give you a reasonable prediction. So unless there's like some really new behavior that has come in the last quarter, like there really isn't any need to retrain the models more than say quarterly or so. And so we have back testing, which sort of can give an indication of how frequently you need to retrain the models, and we're probably retraining the models more frequently than we need to be.
Okay. Thank you.
Perfect. We'll take one more. That's when nobody stands up. When I say one more, nobody shows up. Okay. Anyways. All right. I think we're good to wrap up today, guys. I'm so happy you all stayed back. Thank you so much for coming. And thank you, and Dave, for your time. I know it's going to be a drive back, but thank you so much for staying. And again, it's openness of customers like you who share their learnings and honest feedback is what makes products good. So thank you. Thank you all.
Just to reiterate, as Sanjay said, thank you for coming, and looking for the next session to be in the February timeframe. This is the first of many. Cannot thank you enough for showing up. It's you all that really makes this happen. And each one will be better than the next. We're going to learn from our pluses and our mistakes. You will receive a form. I'm sorry. Yeah, roses and thorns. Hopefully more roses. I'm more of a pink roses guy, but to each of their own, correct? So you'll be receiving a form, short questionnaire. Feel free to be as open as you want. What you liked, what you didn't like, what needs to be improved, and we'll learn from that. We'll make the next one better, and I can't wait to see you next time. Thank you so much. All right. Good job, man.
Thanks.
Good job.